We're back. The third and final talk of this session. We've got Rich Gregg from Philips Healthcare talking about big data reveals insights for lead importance in ECG interpretation. Go ahead, Rich.
Thanks a lot. Good afternoon. It's afternoon here, Eastern Massachusetts. Ting Yang is the main author for this talk, and she moved on to a new job, but I'm presenting for her. And the paper is actually published already, so you can look to the Red Journal to look up the paper and take a look at some of the figures. So again, big data reveals insights for lead importance in ECG interpretation. And the question is, what is lead importance when interpreting ECGs? And the main source of information is the cardiac electrophysiology and the lead placement. So in this slide, on the bottom left, we're showing what the view of the heart, how the heart sits in the frontal plane, and where the lead angles are in the frontal plane leads compared to the heart and atria and ventricles. And then in the middle, the heart, how it sits in the chest, and where the chest electrodes are relative to the heart from the frontal plane view. And then on the bottom right, we're showing the horizontal plane. So looking from the head down to the feet along the spine, and you see the cut through the body and how the heart lays in the chest compared to the chest electrodes. And so that's our main source of information about when a lead is important, what the sort of camera view is for that lead. And a couple of very obvious examples. So acute anterior myocardial infarction, there you worry about ST elevation in the anterior wall, and leads V3 and V4 would be the most important. Or acute inferior myocardial infarction, you would look for ST elevation in lead AVF, lead 3, lead 2. So that's the physical location. And then there's also the cardiologist experience. And my impression of watching cardiologists read ECGs is that it's like recognizing a face, that it's just immediate. There's no analysis, it appears to me, no analysis of measurements. It's just immediate recognition, and then maybe some confirmation with looking at specific parts of the ECG. And then there is some personal preference in the ECG criteria that different cardiologists use to say confirm what they think the pattern is. So that would be another source of information, what leads are important. But that's qualitative information. And what we would really like is to quantify the lead importance. So can we do that? Can we quantify lead importance? And of course, there are many ways, but the way we decided to do it for this study was by developing a single lead algorithm, and we would measure the performance of that single lead algorithm, and then that would become that we would use that as the lead importance. And the type of algorithm that we're using in this method is a search for similar ECGs in a large database, and then we use the interpretation from those similar ECGs to interpret the new ECG, the new unknown ECG. So we do a similarity search for each lead one at a time and test the algorithm for that lead. So here's just one quick example. Here's an example, we would call it a query ECG, or this is the new ECG. And this is the average beat, lead 1. And then we would look to the database for, let's say, the top 5 similar ECGs. So I'll just cycle through what we found in our particular database for this example. So top 5 most similar, lead 1. And as I cycle through them, you could see that they're fairly close. Not exact, of course. This one seems to have a little delta wave, or I think it looks a bit like a delta wave. But cycle through them, they look fairly close. So we would compare the interpretation with the reference annotations to what we get with our algorithm, and calculate the performance of each single lead as a separate algorithm. And our analysis pipeline, simplified analysis pipeline, looks like this. We, upper left in the block diagram, we extract the representative beat, and we align by R peaks, and we use our 12 lead algorithm to get the average beat. Then we normalize each lead in amplitude, and then we apply a sigmoid function to squash the higher amplitudes. And then finally, we find we look through the database and we calculate the L2 distance between the signal that we have and the other signals in the database. Of course, there are ways to speed that up, but the simple way to view it is we look at every ECG in the database, we calculate the L2 distance between that lead we're looking for. So the interpretation is based on similar ECGs for each lead. And we're going to evaluate the performance of each lead based on the F1 score. And that is the harmonic mean of the sensitivity and positive predictive value, according to this equation. And then we normalize the F1 scores of all of the ECG leads. In this study, we're looking at morphology-based abnormalities, and the list of abnormalities is shown here. And again, we're looking at the average beat, so we can only look at morphology abnormalities. We can't look at rhythm. The database we used consisted of approximately 146,000 de-identified ECGs from a single hospital. They were retrospectively collected over a 3-year period, no exclusions, and there were multiple ECGs per patient, and the exact numbers are unknown because it was de-identified. And then in terms of the reference for this database, the computer interpretation was corrected as part of the standard care. And see, here we see results. And here's one example, left bundle branch block. A simple example to start where we really know what to expect for the leads that would be important for calling left bundle branch block. So you could see lead 1 is important, EVL, V1, V2, and V6. So those are the leads that we're taught to use to look for left bundle branch block. Another clear example, acute anterior myocardial infarction. And no surprise there, the leads that we call anterior leads, V2 and V3, end up being the most important. That's where we see the ST elevation. And finally, when we look across the whole database, across all of our abnormalities, we get a lead importance that looks like this. And here you see that lead 2 is the highest. But there's really a question of, is this really the best way to look at it? Because it depends on the prevalence of the abnormalities in our database. So they all get summed up by the prevalence. So some abnormalities are not really going to show up in this plot. So we would like to quantify the lead's importance based on the list for each abnormality. So what we're talking about here is, well, what leads appear in the top 3 list? What leads appear in the top 6 list? And simply counting the occurrence of a lead in the top 3 or top 6 list doesn't necessarily help, because a lead could appear more frequently, but with a smaller lead importance and get a falsely high score. So the way we chose to solve that was to summarize lead importance by ranking the leads and then using a weighted lead order. So the most important lead for a particular abnormality, give it a 12. The next, give it an 11, and all the way through 12 leads. So weighted lead order was how we chose to do this kind of lead importance. And here's the result for, say, the top the list of the top 1, the list of the top 3, top 6, top 12. And I think the surprising part, the top 1 that lead AVR and V4 come out as the top leads across abnormalities. But then I think even more surprising is the top 3 list and the top 6 list, where AVR is the top lead compared to the other leads. And then also when you look at the top 12 list, AVR is one of the top leads, excuse me. And I just wanted to emphasize that by coming back to a table here. And this is a table of the exact lead order for a group of abnormalities. We called them conduction defects that we put together. And if you look at the matrix, we have the abnormality in the rows and the lead order in the columns. And then each row is actually split into 2 because in the paper that Ting wrote, and it's published now, there's actually 2 databases represented. There's the database we're using, the MN, that I already talked about, and the PTB database as well. So the striking thing is that when you look at the lead AVR in red, that it does appear in the top 3 very frequently. And even when it's not in the top 3, it's certainly in the top 6. Now, I want to compare to other studies lead importance. And there was another recent paper, 2020, called Detection and Classification of Cardiac Arrhythmias by a Challenge. And they used a deep learning neural network model. So the focus of their paper was not single lead models, but they also generated single lead models in addition to their multi-lead models for predicting 12-lead interpretation. And they didn't have that many morphology categories, but they did have right bundle branch block and left bundle branch block. So we could compare our results and their results. So they used a similar strategy where they defined the lead importance as the single lead algorithm that did the best for that morphology. So for right bundle branch block, their top 3 most important leads were V1, V2, and AVR, compared to our top 3, V1, lead 1, and AVR. So V1 and AVR in common. And then for left bundle branch block, they had lead 1, V1, and AVR. We had lead 1, V1, V2. So there we had lead 1 and V1 in common, the top 2 in common. So we got similar results to that other paper with a different algorithm strategy. So to summarize, we proposed an algorithm to generate lead importance for each category of abnormality. And we feel like the lead importance does represent the annotation preference to some extent on the database that you use. And finally, a bit of a surprise that augmented lead AVR should not be ignored. It appeared to be one of the most important leads. Now, on the other hand, it doesn't mean that we can actually look at AVR and always get the best result. It means that our algorithm got the most information out of AVR. So we should note that caveat. And on to questions. Thank you.
Very interesting, Rich. I would have never guessed that the lowly AVR was so full of information.
Right.
All right. So first question here: how can you explain that leads that are not really measured but derived seem to contain more information than the leads they were derived from? Which is a reasonable question. Should we conclude that the neural network did not learn the derivations itself?
So I guess I would say that we have the derived leads, I assume, that look in a more important direction. I mean, I guess you would say that if you look at the case of AVR, well, it's really its direction is between lead 1 and lead 2, and it just happens to be opposite. So I would just assume that the polarity doesn't really matter, and that you get more information from that direction in between lead 1 and lead 2 than either lead 1 or lead 2 on its own. So that's how I would explain it.
Sure. And then Roger asks, why do you think lead AVR pops up like that? And then parenthetically, it's not a surprise to me, actually more of a confirmation what we saw in the Basel data set. So I'm not sure if you want to add more to what you already explained to that.
Sure. I mean, I guess that, again, that direction, people talk about it being coincident with the sort of the main axis of the left ventricle. So, when you're looking at circumferential ST depression, for instance, AVR is the important lead there. And when that ST depression is throughout the ventricle. So that looking down the barrel of the left ventricle, I guess I've heard people say.
Sure. I know a lot of times in my own reading of ECGs that AVR oftentimes, I mean, you expect it to look similar to V1, and if it's not, then either V1 or one of your limb leads are misplaced, or in the case of a limb lead, it'd be some kind of a swap, which you would normally detect, through other methods as well. Okay. All right. So I don't see any more questions here. So with that, we can wrap this up. Again, I want to recognize Joel Shu, who organized this session and brought these speakers together. And it's unfortunate he wasn't able to actually do this, because he would have done more justice to introducing these speakers. Since this talk was a little bit shorter, we'll entertain this last question that just popped in. I'm wondering how you interpret the PTB ECGs. I think that they have been made around 2 days after the acute event. Oh, that's interesting.
I mean, I guess we, for instance, when we looked at that acute anterior MI group and acute inferior MI group, we did actually lump what you would call acute and recent together. So, I mean, I suppose that's part of it, in that that we would lump those together. So we still would call some ST elevation and inverted T waves and Q waves. We would still call that in our acute category. Similar for the inferior. So that would be how I would explain it. I know that the prevalence is much lower than the database that we were using from the single hospital. That's about all I know about it, though.
Okay, thanks. So with that, we'll end this. I was asked to make sure to remind everybody to stick around for the poster session, which immediately follows this. So we will end this broadcast, and you can log on to the poster session broadcast. Thanks again, everybody. All right. Nice work, Rich.
Thanks a lot. Thanks for the intro.
All right. See you later.
Bye.